Yeah.
Mohan sir,
Yeah, yes, ma'am. Start
ஆக்சுவலா
பண்ணி
மேமோட ஸ்க்ரீன் ஷேர் ஆயிட்டு இருக்கறதுனால போட்டோ எடுக்க முடியலன்னு வச்சுக்கோங்களேன்.
ஓகே.
கேலரி மோட்ல வர முடியல.
வந்துட்டாங்க அவங்க.
ஓகே. இப்போ தெரியாது சார்.
ஓகே. ஸ்டார்ட் பண்ணலாமா? Good evening and welcome to Open Seminar on Medical Image Processing. I formally welcome to our department staff and the students to this open seminar for medical image analysis. So I would like to invite our chief guest, Dr. E.Priaya Madam, Professor Department of ECE, Sairam Engineering College. I would like to welcome all our department staffs and students and once again to this seminar. To utilize this seminar for what is the medical images, how they are going to utilizing. This will be going to give very brief introduction to our chief guest, Dr. E.Priaya, Professor of EC Department in Sairam Engineering College. I would like to introduce our chief guest, Dr. Priya ma'am. Priya ma'am is a professor. She is working the EC department in Sairam Engineering College. She has B degree in Electronics and Communication Engineering from the University of Madras and the ME degree from Madras Institute of Technology, Anna University. She received her PhD in Biomedical Engineering from the same university. With a 20 years of teaching experience, she is currently guiding the student in the area of biomedical modeling and image and signal processing. Her research interest is including the biomedical image processing and signal processing and application of artificial intelligence and machine learning technique. A recipient of DST Pure Fellowship, she has published several articles in the international journal and conference proceeding, as well as book chapter in this area of medical image and infection disease. She served on a editor review board of International Journal Information Society and Privacy, IGI Global. She authored the book Hybrid Image Processing Method of Medical Image Examination. This book is published in CRC Press. Um, she received the AIST Research Promotion Scheme grant for project title of Artificial Intelligence Enabled Comprehensive and Portable Public Health Care Screening System for year of 2020 and 21. She have the very good experience in the medical image processing. Now I am going to hand over the session to our chief guest, Dr. E.Priaya, Professor, EC Department, Sairam Engineering College.
Thank you, sir. Thank you
Thank you,
for
ma'am.
introducing me, sir. Thank you, sir.
Thank you, ma'am.
I thank the organizers and I thank the HOD and I thank the faculty fraternity for giving me an opportunity to deliver a lecture on medical image analysis. Probably I share my screen now. Hope my screen is visible.
Yes, ma'am.
Yes, ma'am.
Okay. So I have organized my presentation like this, simple introduction and some basics, probably on image sensors and modalities, and a very simple case study for this evening. So to start with, I thought I'll start with a fact, like say among the information that is transmitted to the brain, 90% of the information that is transmitted to the brain is of a visual. So that's a quite huge amount of percentage. So all the information that a brain perceives is in spite of visual information. And you know that most of the people, almost 40% of the people, they respond for any visual information that is given to them rather than any text information. So that is another appealing perception. And you know that in most of the social media where we look into, we are more attracted towards the visual photographs or any visual data present in the social media. So it says that about 96.7 percentage people are being attracted by the visual information from the social media. So this is the huge um, uh, appreciation or the background behind the visual perception. So I think I should not forget to quote this proverb: "A picture is worth 1,000 words." So this image on the left is very familiar, and it says that the text information is embedded in the left image, whereas on the right you see that starting from Stone Age to the new age, probably the industrial era. Okay, and later on you see that like we have started wearing masks these days, isn't it? So that is also depicted. And you know, finally people start trawling and they carry oxygen cylinders. Now that is the era to where we are being pushed these days. Okay, so due to pollution and things like that, and because of all these pandemic period, we have been even forced to carry oxygen cylinders. So those things are well presented, even though text is not there. Okay, so that is the beautiful or beauty of visual perception. Now, with this background or basics, I thought I'll start with medical imaging. So, imaging is so this is the power of imaging. So we have seen the power of imaging, isn't it? So, having seen the power of imaging, we'll see what medical, because this presentation is all about medical imaging. So, medical imaging actually aid in visualization of anatomical structures. Even they give information regarding functional metabolic activities of a human. So all these convey not only the nominal characteristics of a human body, they even convey the abnormalities present in a human body. So in this way, this helps the physician or the doctors for accurate diagnosis. So the main goal is to prevent and cure, because you know that prevention is better than cure. So that is the main background behind this medical imaging. And the main purpose is, like, say, for example, as we saw that image is more than 1,000 words. So imaging, all medical images convey good information, so out of which enough inference could be arrived by the physician or the doctor. So that way it is more simpler and more convenient. And since it deals with human beings, this study should be more ethical. So only after proper ethical clearance, even imaging could be done. So that is very important. Okay, so that is a goal and purpose of this medical imaging. So probably I'll start with image, very basic fundamentals, okay, and I'll not go much in deep all these fundamentals, just a brief intro, and then let's move forward. So what is an image? So it's all depends on the small picture elements that you see here, okay, the smallest element. It's called as the smallest element of an image, okay. So all these represents the picture elements. So closer the picture elements, better the resolution. So that is the idea behind the image. So if the pixels are now these images for further processing, once these images are acquired, it has to be stored in a PC or a computer. So when it is stored, it has to be stored in some bit formation. Probably if you start with a basic 8-bit formation, then you get, because it's a computer, so it will be stored in power of 2. So if it is 2 power 8, then it is 2 to 6 combinations. So grayscale ranges from 0 to 255. Now all these values of pixels directly correspond to the intensity of the light that is striking on that particular elements, basic elements, that is the pixels. So this is about these pixels. And now here a small image, I've shown a small image which represents the letter 8. Now as you zoom in, you could see some checkerboard patterns are visible here. All these small checks are nothing but the picture elements. So as I told you here, it's not that much visible. The letter 8 is not that much clear, isn't it? So if the checkerboard pattern are much closer, probably the resolution of the image could be better. So normally the dimension of this image will be referred as the number of pixels present along the height multiplied by the number of pixels present along the width. So if x is height and y is width, the total number of picture elements will be x into y. So that is the power of this pixels. Say for example, if there are 24 pixels are present across the height and 16 along the width, then the total will be 24 cross 16 pixels present in the image. So here, as you zoom in, you could see some numerical values. So these 0 represents the darker pixels. So as I told, the 8-bit pixel, the grayscale ranges from 0 to 255. So these zeros present refers to the dark shade of the grayscale. Probably the white portion refers to 255 or values closer to 255, where they represent the lighter or the white shades. So these are the different shades of the gray levels, ranging from 0 to 255. So behind the image, there are these new numbers present. So actually, it's a matrix. It's a form of a matrix. Image is a form of a matrix. That's it. So this is how it could be even stored in a computer. So that is the importance of this images. Similarly, earlier I was talking about grayscale images. Now it's the same. If it is a color image, say for example, this is a image of a dog. Now this actually again comprises of 3 basic channels or the primary colors RGB. So these are the 3 primary channels out of probably in this case the total number of pixels present would be the total number of pixels present along the height multiplied by the width into the number of channels. If the number of channels, say RGB, is 3, then it will be the total number of pixels will be n cross m cross 3, where this 3, the last number refers to the number of channels. So this way the colored images are stored. Okay, so I just have told the basic color channel RGB. Similarly, there are different color channels present. Probably the primary colors are the RGB colors. So this is how the colored images are even stored in a PC. So a small fact regarding these images. When I said grayscale image, now it has a 8-bit color depth, which means 2 power 8 is 2 to 6 gray scale variations are present. Now for a color image, the same case will be 24-bit color depth. Why it is 24? Because as I said, it comprises of 3 channels. So 8-bit for R channel, 8-bit for green channel, and 8-bit for blue channel. Together, if this is again when represented in terms of 2, it is 2 power 8, 2 power 8, 2 power 8. So you get 2 to 6 cross 2 to 6 cross 2 to 6, which is approximately 16 million colors. So that's why when you see a color image, you find so many depth of information present. So that is the beauty of the color image when compared with grayscales, because grayscales have only 2 to 6 depth of colors present or gray shades present. But for a color image, it has these many million, 16 million colors present. So next, I just want to introduce a small basics regarding this imaging, because as I told, in my presentation, I have some basic introduction and about the image and probably some image sensor principles. And with this, I thought I'll even touch upon the image modalities, probably medical image modalities, and a simple case study. Now here, now what is this beauty of this image sensor? Now I just want to insist, like if you want to visualize an object, it all depends on the size of the object. See, for example, our human eyes could grasp an object if it is in a few meters or centimeters, even up to millimeters, and not below that. If an object is of size, say 10 power minus 3, or if it is a micrometer, nanometer, then probably it is not visible to a human eye, isn't it? Then in that case, image sensors come into picture. Say, for example, I just have an example here. If you want to visualize a water molecule, that water molecule, its diameter is the order of 10 power minus 10 meter, which is probably even lower than a nanometer, 10 power minus 9. So a human eye cannot visualize a human molecule. So how it is possible to visualize a human molecule? This is the basic mantra. That is, like if you want to visualize an object, okay, then the source or the light source that is used to picturize the particular object, okay, should have the same wavelength or even a smaller wavelength than the object. So this is the basic mantra. Probably I'll throw few more light with this quote. Okay, so we all know about this basic electromagnetic spectrum, isn't it? So here on the left hand side, you see the football field. Suppose if there is a match, cricket match or a football match, something is going on, some live streaming is going on there. So in that case, they use radio waves for transmission or reception.
Ma'am,
So you see that,
ma'am,
sir.
ma'am, this is Vashni.
Yes.
Can you hide
Yes.
that strip, ma'am, in bottom layer card?
In the strip, ma'am.
கீழே bottomல stop sharing
இதுவா
பக்கத்துல hide இருக்குல்ல ma'am.
அதுவா இப்போ
Okay ma'am, now it is visible, entire slide is visible. Thank you ma'am.
okay, thank you. So here probably like as I told, for live streaming they may use radio waves, isn't it? So you could see that the field of football ground usually be represented in terms of meters. So that's why they have mentioned here as radio waves. Now as you move towards the right hand side, okay, you see that the object's size reduces. So when it comes approaches, say bacteria, it is not visible. So all these football ground is visible to human eye. We can see another human being too. Butterfly is visible to a human eye. This pinhead is also visible to a human eye. But thereafter, nothing is visible, isn't it? Bacteria is not visible. Virus is not visible with our human eye. So there need to be some source. See the size of this objects. It is of 10 power minus 5 meters. Everything is in meters. And this is 10 power minus 7, something like that. Even molecules 10 power minus 8 or minus 9. See the size. So for these objects to be seen, okay, you need to use these sources. So that is the thing. So the size of the object should be proportional to the wavelength of the source that has to be used to visualize the object. So that is the beauty of this electromagnetic spectrum. So coming back to our example, that is water molecule. I was telling about this water molecule. Sorry. Water molecule sizes of 10 power minus 10, and it's not visible with human eye, isn't it? Let's come back to this electromagnetic spectrum. You see here 10 power minus 10, isn't it? So probably ultraviolet or X-ray has to be used as a source to visualize the object. And that is what is even referred here in the literature. Okay, so if you want to visualize, so this is the mantra. So what is that mantra? If you want to see an object, The wavelength of the source that we use should be of the same size of the object. So that is the principle of the image sensors too. So this is the mantra. Once this mantra is very clear, then what sort of imaging sensors need to be used, or what sort of source for each of the sensors to be used will be very, very clear. So that is the idea behind this particular slide. Okay, now with this, so I think I've introduced, or I have explained like what is the image, or what is the benefits of a medical image, and how to visualize a particular object, probably even for atoms. Okay, you have to use gamma rays. So that's it. So these image sensor principles, I think I've made it clear. So with this, let's move on to the imaging part, or the acquisition part, because image sensors is a part of image acquisition. So it starts from here. Okay, the instruments that are used for acquiring an image. Okay, now you know that this instrument, okay, so which are used, okay, I told you, isn't it? So the basic, either X-rays need to be used, or ultraviolet source has to be used, or gamma rays has to be used. So whatever, it all depends on the physics of the instrument that is being used to capture the object, or whatever it is. Okay, so some physics comes into the picture of image acquisition. And similarly, like say for example, any anatomical structure, or any physiology of human will be well visualized while the images are being captured. And no, like say for example, if any interventions or any noise comes into the way of acquiring an image, probably uh, pre-processing or filter techniques need to be had, so that it could be used for proper applications. So for post-processing, computer storage comes into picture. So all these, see, physics comes into picture, physiology comes into picture, computers comes into picture. That's why it is called as a multidisciplinary paradigm. So image acquisition actually involves multidisciplinary paradigm. All these physics, physiology, computer, filter, everything comes into action. Now, so probably the way how the images are acquired could be categorized into these three methods. Suppose if any contrast agents are used to picturize any object, then that comes under this internal category. So, and if nothing, if any, no more, or if it is purely non-invasive, then that is what is called as external. So then you have the hybrid method called external and internal. So probably the X-rays, CT, ultrasound, they come under this category of external type of imaging modality. And suppose if any contrast dye is injected, and if images are acquired, then those come under this internal type of category. And then the combination probably is of fMRI, MRI, and perfusion type of MRI, and the EIT, electrical impedance tomography. All these comes under the hybrid method. Probably I'll touch few of these imaging modalities. So imaging modalities, actually they infer some anatomical as well as functional information of a human. So anatomical, these imaging modalities, they convey the anatomical, probably like X-ray, CT, ultrasound, optical tomography, probably a 3D image from 2D slices. So all they probably deliver anatomical information of the structures that are captured. And these functional in the sense like Say for example, like what is the well-being of a human mind, whether the IQ level of the person is up to the level or not. So such functional activities of the organs could be captured with the help of these image modalities. Probably I'll touch few of these. The basic is the X-ray. So probably here you see that a small dose of radiation passes through the body in case of X-ray, and then it is projected onto a film, where this film I have shown here in case of a chest X-ray, and this is in the case of a dental radiographs. So probably these radiations are harmful. And like the next variety is the next type of the external type of imaging modality is the ultrasound. Probably the physician or the technician may use a probe or transducer to receive the sound waves. So from where are these sound waves transmitted? Again, from the same transducer, a piezoelectric crystal will generate these ultrasounds, and probably they will impinge, and then the reflected waves from the anatomical structures received by the transducer could be picturized in terms of an ultrasound. So that is a difference in the ultrasound. So probably the ultrasound captures the tissues, the fat, and there will be a probable distortion in case of a bone. So this ultrasound will can capture um, or probably it can project more information from tissues rather than bones. That is the characteristics of an ultrasound. Probably sonogram is nothing but the image that is produced from an ultrasound. So probably here some ultrasounds which we are familiar to. Okay, so this is the ultrasound image of a fetal. So even stages of pregnancies could be observed using this ultrasound. So that is the beauty of this ultrasound. And then comes the computed tomography, or it is also called as computer axial tomography. And here, here also, it is similar to an X-ray because it also involves radiation, whereas ultrasound does not involve any radiation. So only sound waves, impingement of sound waves are being recorded in case of ultrasound, and that's not the case with CT. Probably here in X-rays, bones are much visible, but in case of CT, even tissues or 3D image of anatomical structure are much more visible in case of a CD. So it is a non-invasive procedure, and it's since it's a non-invasive procedure, it is painless. As I told you, proper anatomical information of any organ or any structure could be well imaged with the help of the CT scan. Here on the left hand side, you see a patient lying on a table wherein the you can see the transmitted as well as the received radio waves by the transducer. And on the right hand side, some examples of the CT images I've shown. Probably the axial view of lung. In case of actually, you see these two lung images, but I just want to show you, this is a COVID CT lung image where you see glass transparent portions that represents the presence of the COVID infection. Whereas on the right hand side, you see some white dots. Okay, so those are the nodules of TB. Okay, so this shows the presence of TB. So all these, abnormal conditions are well visible in this CT. Similarly, brain hemorrhage could be analyzed from the MRI, CT images. And this is a CT image of a kidney, and this is an abdomen. Okay, so probably all the internal organs, tissues, well in liquid, and the solid um, could be well visualized with the help of this CT. And like as I told you, I've just shown the axial view. So which means that there are few other views also: axial, frontal, and sagittal, that is longitudinal. So if the plane cuts the head and feet, then that is what is called as transverse plane. Probably would divide it into superior and inferior. And the plane, if it cuts into the front and back portions, that is what is called as the coronal plane or the frontal plane. Probably the portion that cuts the proximal and distal portion is the sagittal plane, or it is called as the longitudinal plane. So these are the different anatomical axes with which these images are represented. Now the next is the very familiar imaging modality, that is the MRI. Now you know that human body consists of more fluids, okay, liquids present in terms of blood and um, acid form and things like that. So since it comprises of fluid, most of the components is of in terms of H2O. So all the hydrogen atoms will try to process in one typical plane when the human body is under a magnetic field. So when there is a small magnetic field, these hydrogen atoms, they process to one condition. And when a energized coil, okay, so it becomes an electromagnet. When a coil is energized with a high RF energy, and the next pair, when this RF energy is induced, these processed hydrogen atoms are imaged. Okay, so that image is what is called as an MRI. So here again, the same setup, except an magnetic field is present in case of an MRI. So MRI shows again even better information regarding it. It is more actually suitable for spinal, even bony structures rather than the ultrasound. So that is the advantage of this MRI over other imaging modalities. Probably I'll stop with the SPECT or SPECT scan. So because for even diagnosing or cancers, this SPECT or PET scan plays a vital role, as it comes under nuclear imaging. So it's a branch of nuclear medicine which uses the radioactive material. So radioactive material will be injected into the patient before the PET scan is carried out. And after an hour duration, the similar to the MRI or CT scan, this PET scan is done. Now this PET, why it is called as PET scan? Because it images actually the positron, which is an oppositely charged particle of an electron. So there's an impingement of this positron over the film produces this PET scan. The one single difference between this PET and SPECT, I have the next thing is, the next modality is a SPECT. The difference is here they use gamma rays, whereas there they use here a single photon of these gamma rays, okay, will be used. Probably I'll show you the PET scan. Here you could see that this is the cancerous cells. Usually the cancerous cells will eat all the contrast dye that is injected rather than the remaining tissues. So that's why the cancerous tissues will be well visible in a PET scan. So that's why this PET plays a vital role in diagnosing cancerous tissue. Okay, so if a gamma camera is present or a PET receiver is present, that receiver or a receiver could capture this PET information. Okay, so but this PET, though we say they use a radioactive material, it is actually not a harmful, because over a period of time it starts decaying. Okay, so when the patient urinate, actually all these radioactive materials will be removed from the human. Okay, so that is the beauty behind this PET scan. So having learned all these imaging modalities, probably I have a diagram wherein I'll show you the the image analysis, the medical image analysis. Before any analysis to be done, the main thing is processing. So any medical image involves these many processing. So only with the help of this processing stages, analysis could be arrived at. Without these processing, any final analysis could not be arrived, like whether any particular tissue has any abnormalities or any problem, whatever it is. So any analysis will not be arrived if proper processing is done. So probably I thought I'll demarcate the processing stages like this. So initially, as I told, it all involves with the image acquisition. Probably digitalization comes into picture if the images are to be stored and processed later on. And you know that the instrument that is used for capturing the images need to be calibrated. So that is very important. Even when we use a small instrument in a lab, we calibrate and use it. So here calibration plays an important form. And registration. Say for example, in case like a tumor position could be identified, probably if it involves more than um, um, two or multiple detectors used. In that case, this image registration comes into picture. Image registration actually finds out the proper location, because it builds up the formal image from the given information. So that way registration plays a vital role in finding out the inference from the available sensor details. So probably all these information without any filtering, it could not be one cannot arrive at an inference, because while the images are being acquired, like probable noise could also be it also will be entered in. So those things have to be filtered. And similarly, if one information, or if the information in one of the domain is not visible, probably in another domain it would be visible. Say for example, if in time domain, if certain information are not visible, we move on to a frequency domain, something like that. And similarly, time frequency domain is much more informative rather than time or frequency domain. That's why we move on to transformation domain, wherein the features could be extracted. So time frequency domain features are more informative than spatial domain or the frequency domain, so that it helps in classification or interpretation of the results. And you know that the pre-processing, apart from these filters, okay, they one of the prime is the illumination. See, I was when I was telling about the image sensor details, I told that for capturing a particular image, certain sensors need to be used, and for those sensors, some light sources or energy need to be used. It could be a gamma, it could be an IR, it could be an ultraviolet, or it could be a radio waves too. Okay, so when any sensors comes into picture, this illumination plays a vital role. So I thought I will especially point out a particular case study from this component. So as a whole, for any image analysis, all these blocks are very, very, very important. Okay, so stage by stage, they play a vital role. So now I thought I'll just concentrate on, maybe I'll finish off my talk with this a small case study with respect to this illumination. So, because my area of research is on medical imaging, and especially on framing out an automation in TB diagnosis. So, TB is a highly infectious disease. Everyone knows that it is very highly infectious, and uh, if one person is affected, and if another person is in the uh, same surrounding, okay, within a small distance, then if the first person sneeze, cough, then the second person is highly prone to get infected with the help of with this TB. And you know that this is a bacterial infection, but whereas COVID is a viral infection, this TB is a bacterial infection, and this resides in the alveoli of the lung. So this is the air sacs. Okay, this is what is called as alveoli, and the rod-like structures that you see here are the bacilli. That is the disease-causing, tuberculosis disease-causing agents. And I'll show you the image of a TB. So how to capture a TB image? First of all, sample need to be collected. So from where the samples are collected? From the saliva. So a person will be allowed to cough and then expel the saliva, and then that saliva will be collected, smeared on a slide, and it will be, because see, the size of this bacteria will be in micrometer. All these micrometer length objects are not visible to the human eye. So it should be visualized only under a microscope. So, you see, this is the TB image. Can you see so many white, small structures you see here? All these are the disease-causing bacteria. So, how many bacteria are there? You know what happens? The technician, when he views this particular slide under a microscope, he has to count the number of bacilli, because World Health Organization says that depending upon the count of this bacteria, the slide can be graded into 1 plus, 2 plus, 3 plus, or TB negative. If there is no bacteria at all, if it is very plain, if the image is very plain, then the slide is TB negative. Or the technician has to grade it as, if the severity is mild, probably it is called as 1 plus, medium 2 plus, severe 3 plus, like that he has to. Counting these objects is it is not that much easy. You know that the technician takes at least 40 minutes time to view a single slide. Okay, so it takes that much time. You know that again, this is very highly infectious, and this technician also, he or she is prone to this infection. So thereby automation comes into picture. Without the intervention of human being, if automation could be done, that is a very good understanding. So that is what is actually is expected from any medical imaging field. Okay, automation, wherever you go, the doctors or physicians are crazy about this automation. So automation will be fulfilled only with the help of engineers. Engineers play a vital role in creating automation, or they assist the physicians actually. Okay, so I've taken a portion of this TB sample. There you see these are the rod-like structures. Now, if I could draw a line and plot intensity, because already I think I've told what could be behind the image is nothing but a matrix of some numbers, isn't it? White patch will show you a number ranging around 255. Probably a black will show you a pixel in the range of some zeros, something like that. So here what I've done is I've drawn a line over a line in this image, and if I could uh, draw intensity profile, my profile will look like this. Okay, so here in this line, I could see some three white objects present, isn't it? So these are the bacteria. Actually, these are the bacteria, white, white. So if I draw a line like anywhere I can draw, I have just simply drawn a line like this, just to see how the intensity. So intensities are. So I could see some um, um, spike here. Okay, the first object that you see here, probably another spike for the second object, the second spike, and you see another object at the end, probably a small spike at the end. So this is what is called as a 2D intensity profile, and probably a 3D intensity profile can also be derived at. Okay, you see there is a this baseline is not straight, isn't it? Similarly here also there is a curvature. This baseline is not straight. So this is that illumination component which I was talking about here in this diagram. Okay, illumination. I told I'll concentrate on this illumination part. Okay, so because of the optics of the microscope, there will be a small white patch that actually I'll show you. There is a white patch here which is not that much visible. When I show the corrected image, probably you could recognize the removal of that white patch, which is nothing but the illumination component, and that is introduced because of the optics present in the microscope. Okay, so probably this baseline wandering is because of the illumination component present in the image. Okay, now here there are many techniques. This is one such technique wherein decomposition method could be used. So what is this? I think now this image is clearly visible, isn't it? So this white patch is removed here. This is the processed image. Okay, so this decomposition method actually has removed this. So how? In what way it has removed? So this decomposition procedure, what it will do, it will decompose. So see, this white patch that you see here is a very low frequency component present in the image. So if there is no variation at all, it is nothing but a low frequency. If there are variations, it is nothing but a high frequency. So in an image, if the white patch that you see here in the image is the low frequency component. Now what this decomposition method will do is this decomposition method will decompose depending upon the variations present. It will decompose the image into so many components. Okay, so probably the low frequency components are the patches. So if you remove the low frequency components and reconstruct the images with the remaining, probably you will get this processed image without this illumination component. Okay, so probably this is the 2D and 3D intensity profile after for the processed image. Sorry. So this is the processed image. So again, if a line is drawn over here, okay, so you see this is the first object, the second object, and the third object. So you see that the baseline wandering is corrected here. Similarly, even in the 3D profile, the baseline wandering is corrected. Okay, so that is the beauty of this post-processing. Especially here, I've used this bi-dimensional empirical mode decomposition for removing that illumination component. Now, I said some portions of the low frequency components. So they are called as the intrinsic mode functions. These are the IMFs. So here I have removed these IMFs and reconstructed the remaining IMFs are reconstructed. So to get back this particular image, the processed image. So this is one such medical image processing wherein this illumination component could be corrected. So probably if you have a chance and working with images, it is quite interesting because there are, as I told you here in the flow diagram, there are numerous era wherein one can venture and work on it. So there are so many avenues where people can work in this medical image processing. Probably I'll stop with my presentation. Thank you. Thank you for listening. Thank you,
ma'am.
sir.
Thank you, ma'am. Thank you, ma'am. So
Okay, sir.
formally, I'm going to give a vote of thanks. Good evening. I would like to thank our management, principal, vice principal, HOD of EC to given the such a good event like a medical image analysis, uh, medical image analysis, to given the chance to conduct the event. Would like to thank our chief guest, Dr. E.Priaya ma'am, to given such a good information about the medical image of this evening. Like she started for the signal, that is frequency itself is giving the very good example as well as of information about the images. I would like to thank our staff member and the student. I think students are now gathering the information about the medical image, where they are using, how the medical images are captured, what is the future in the medical image, everything they are going to understand. I thank you all. I thank once again to our guest, Dr. Priya ma'am. Thank you, ma'am.
Thank you, sir. I thank the
Thank you, ma'am.
organizers, HOD,
Thank you, ma'am.
and the team members. Thank you, sir. Thank you. Thank you all.
Thank you, ma'am. Thank you, ma'am.
Okay,
Thank you
sir.
so much, ma'am. It was excellent presentation. Thank you,
Oh,
ma'am.
thank you. Thank you, ma'am. Thank you. Sir, I'll leave, sir.
Thank you, ma'am.
Yeah, yes, ma'am. Thank you, ma'am. Yes, ma'am.
Okay, sir. Okay,
Much.
sir. Thank you. Thank you. Thank you.
Thank you, ma'am.
One, sir. Thank you, sir. One, sir.